All right, I just really quickly want to close out the example that we did in class today. It should be pretty plug and chug, but I wanted to just make sure that we were complete in our calcs. So I have here the overhanging beam that we were discussing in lecture. A few things to remind everybody about. First off, we have here the equation for bending moment. And remember, in terms of our areas of validation or where equation is valid, this is valid from x equals 0 to x equals 30, if you remember, because if we look at the beam, that's going to be valid anywhere from this support where x equals 0 all the way to this support right here, x equals 30. Remember, just because we have a brace right here doesn't mean that our loading conditions or our boundary conditions on the beam has changed. Again, it's still one fluid continuous parabola from x equals 0 to x equals 30. Now I have here below the moment diagram, and if you look, the values in red are the values that we computed in class. Now, just to make sure everybody's clear, these values over here on the right were not computed using this equation because, again, in this overhanging region we used m equals minus x squared because we cut a section and looked to the right. But everything in this left parabola from x equals 0 to x equals 30 can be computed using this. And so far we had only computed two values. We computed the 70.31 there on the very, very left, and then 112.5 right here. Now, the way that worked is what we did is we went into the equation and we plugged in our x values. So what I thought I would do is go ahead and remind everybody that, remember, over here at the support, this is x equals 0, and x equals 0 goes from there. So this is 3.75, 7.5, 11.25. And the reason why that's relevant is because now we're going to have to look at this central segment, and we're going to need to compute moments right here, right here, right here at our quarter points. And then we're also going to have to determine M max. So the first thing I ought to do is determine those quarter point x coordinates. So all I'm doing is I'm just using, remember, the LB is 15 feet, so a quarter of that's 3.75. So I'm just adding 3.75 to each of these dimensions. So this one, of course, is 15. 3.75 from that is 18.75. Whoop. 18.75. This one right here, that one is 22.5. This one is 26.25. And then adding 3.75 gets 30. Okay, and remember, this equation that you see here above, this is valid all the way from x equals 0 to x equals 30. And so ultimately I want those quarter point moments. Now I have I sort of blew up that central region over here on the right so that I could just focus on that. So again, what I want are these values. So at the very least, I need my quarter point values, but I'm also going to need to determine M max. I'm going to show you how I'm going to do that here in a second. First off, let's do MA, MB, and MC. So for MA, all I'm going to do is plug in x equals, what is that, 18.75? So 22.5 times 18.75 minus 18.75 squared. And then for MB, I'm going to do 22.5 times 22.5 minus 22.5 squared. You can probably see what's going to happen there. And then MC, I'm going to have 22.5 times 26.25 minus 26.25 squared. Now, when you chug all this out, what you're going to get is you're going to get a positive value for MA. MA comes out to be 70.31. MB, now if you look at the equation, MB got 22.5 times 22.5 minus 22.5 squared. So it actually comes out to be 0. And MC comes out to be actually negative. It comes out to be negative 98.44. So just to make sure I'm locating those values on the plot, this is 70.31, this is 0, and this is negative 98.44. Now that's MA, MB, and MC. Remember, when we plug it into our expression at the end, we always take those as positive values, so we always use the absolute values. But for M max, it's actually not as straightforward. With M max, the question is, do I use this value or do I use this value? Well, the only way to know that is to compute both of them and to figure out which one I need to use. So if I do that out, so I'm going to have M at x equals 15. So I'm going to plug in 22.5 times 15. Plug in the x for 15 minus 15 squared. And then do the same thing at x equals 30. Again, by looking at the segment, you can see the maximum moment is either going to occur on the left or on the right, but you might not actually know which one until you go through and chug it out. Now, when you do, when you plug and chug these equations, you're going to get this is 112.5, and this one is negative 225. So, just to put that on my figures here, this one, that one's 112.5. That is minus 225. Okay. So when we compute our CB expression, remember we take positive values. So first off, C sub B is, and our formula is 2.5 times M max plus 3MA plus 4MB plus 3MC, all under 12.5 M max. So first off, for M max, what is the M max value that we're going to use? Well, we either use 112.5 or negative 225. The big thing to remember is that you're always looking at this from a magnitude perspective, and which number has the larger magnitude? It's 225. Remember, you're always using absolute values here. So this is 12.5 times 225 over 2.5 times 225. And then for your remaining moments, you've got those values here. This is 70.31. This is 0. And this is 3. And then remember, we use positive values, 98.44. And so when it's all said and done, you should get a CB value when you plug and chug this of 2.632, or we just use CB is 2.63. We typically, 2 decimal places is usually good enough for a CB expression. Okay, so in our next lecture, we'll see where CB is used in our computation of flexural capacity. But for now, all I'm interested in is that you can accurately compute CB. And you've got a little more practice to deal with on your homework. That's all I have, everybody. I will see you next time.